Yeah, thank you very much. So this is a common work with my colleague Matthias Holschneider from Potsdam, and we are interested in the size of the largest expected earthquake magnitude in relation to induced seismicity. So, okay. So it is well known that fluids can trigger earthquakes. This is more or less the topic of this session here and also of the union session on Wednesday. We also know that at least in some cases the resulting seismic hazard cannot be neglected. For example, we have seen the EGS experiment in Basel 2006, which has been mentioned several times here in this session. And in this work, we aim at estimating the magnitude of the largest expected earthquake in a time interval at a fluid injection site. The main problem in this context is the problem of data availability, because data are usually recorded during commercial activities and are therefore not available. I will come back to this point later in this talk. So our approach is statistical modeling of induced seismicity, and here we use empirical knowledge, which is expressed by probability distributions for earthquake magnitudes and also earthquake rates. We use furthermore extreme value theory because we are interested in a maximum earthquake size. And finally, we use methods from Bayesian inversion because we are interested in estimating parameters and especially their uncertainties. And for this, Bayes theorem is a quite convenient and useful tool. So the assumptions which we are making in our analysis: first, we assume that earthquake magnitudes follow the Gutenberg-Richter law, so basic assumption. Second, we assume that earthquake numbers or earthquake rates are consistent with a Poisson process with time-dependent productivity, so we have a non-homogeneous Poisson process or non-stationary Poisson process. And finally, we assume that the productivity of induced earthquakes is proportional to the fluid injection rate. So, first of all, we have to model the fluid injection rate, and this is done in the following way here, in a general context. We assume that at some point the injection of fluids is switched on here and reaches after some time a saturation value or approaches the saturation value. And this overall behavior can be modeled quite conveniently by the function arcus tangens. So we use here for the fluid injection rate, the function f of t is a times arcus tangens bt. And this comes with two parameters. The parameter a is more or less the saturation rate, which is shown here. And the parameter b controls the time to saturation, so how fast or how slow this saturation value is approached. So now I can show you the statistical model which we use. First of all, we have here on the horizontal axis the time, and on the vertical axis the earthquake rate. And what we see here is decomposition of time into two periods. First, we have the pre-injection period, where we have only natural seismicity, which is described by the natural seismicity rate lambda 0. And then we switch on the injection, and the earthquake rate increases according to the formula I showed you on the previous slide. And we have the following expression here for the earthquake rate. So we have lambda 0 plus c times the injection rate as a function of time. And c is the factor of proportionality between fluid injection rate and rate of induced earthquakes. So for these two periods, we need to have a catalog, or at least some information from an earthquake catalog, that allow us to train our model and to estimate the unknown parameters. And then, if we have trained the model, we look into the future, which is given here by the yellow box, and we are interested in estimating this quantity mt, which is the magnitude of the largest expected earthquake within this time interval, within this finite time interval of length t. So this is the basic setup of our statistical modeling approach. So the case study we perform is done for the Paradox Valley site in the US. And this injection site is shown here on this figure, which I stole from the publication of Aki et al. In BSSA 2005. So I'm not an expert in this injection activities. The general goal is that we have here the Dolores River, and from this river aquifer brine is extracted, and after treatment it is re-injected again below surface under high pressures. Some information about the seismological things is given here, or are given here. Details can be found in the publication of Aki, which I mentioned. So we have here a local network that records earthquakes with a magnitude of completeness of 0.5, starting in 1985. During the pre-injection period, which lasts for 6 years, we have only 6 earthquakes, so on average 1 earthquake per year. And in the first part of the co-injection period, we have about 1,400 earthquakes in 1,100 days. And in the second part of this co-injection period, we have about 240 earthquakes in 332 days. And in this second part of the co-injection period, we observe a relatively large earthquake with magnitude 4.3. So we are doing here a retrospective analysis, and for this aim, we define this last part of the co-injection period as the future period in quotation marks. So we use the first 2 time intervals as a training period for the model, and then we look into the future and see whether our statistical model is somehow consistent with this observation of a magnitude 4.3 earthquake. So some words about the Bayesian inversion technique. So Bayes' theorem includes 3 parts. So for the unknown parameters, we need to have prior distributions. Then we have a likelihood, which includes the data, so the earthquake catalog. And we end up with a Bayesian posterior distribution, which gives probability which is a probability distribution for this quantity mt given the data. So we have here 3 free parameters. So this is lambda 0, the rate of natural earthquakes. This is c, the factor of proportionality between fluid injection rate and induced earthquake rate, and we have the Richter B value. Since we have no prior or no additional information on these parameters, we just use here a flat prior, which is a non-informative prior in terms of Bayesian terminology. And then we can calculate, using Bayes' theorem, the Bayesian posterior distribution. So we need the following input data, and this is more or less the reason why we used here this, site of Paradox Valley, because all these input data are available in the publication of Aki et al., although we do not have access to the data. So we need not the full complexity of the earthquake catalog, but we need certain measures from the earthquake catalog, and these are listed here. So we need to know the pre and the for the pre and the co-injection period, the durations and the earthquake numbers. Additionally, we need for the co-injection period the frequency magnitude distribution. This is also provided in this publication. We have a binned frequency size distribution. And finally, we need the injection history. And this has been calculated as I showed you before. So with this at hand, we can calculate the Bayesian posterior distribution, which is given here. So this is a probability density function. Here we have MT, the earthquake magnitude, for this time period of 332 days. And on the vertical axis, we have a PDF, and I also show you here confidence intervals color-coded. So it's always difficult to compare a probability distribution with a single value. So we want, or as I said before, we wanted to focus on this magnitude 4.3 earthquake. And what we can say is that this magnitude 4.3 earthquake, which occurred in year 2000, is found at the upper end of the 95% confidence interval. So if we start with 95% confidence, which we want to have, of 5% error probability, then we can say, okay, our upper bound of the confidence interval is this magnitude 4.3, which has been observed indeed during this time period. So it is always a little bit questionable to perform this retrospective studies, as I mentioned before, because the target quantity or the future, in some sense, is already known. And one might speculate that this can be, the desired result can somehow be achieved by adjusting some parameters, but this is not the case here. I want to emphasize that all parameters here in the study are estimated from the data by using Bayes' theorem. So there's no free parameter which allows to adjust, in some sense, these results here. Second, we can calculate for a given maximum tolerable earthquake the fluid injection rate Fs, which must not be exceeded. So if we imagine that we have an injection site and for some reasons we want to have a maximum earthquake size of, say, magnitude 3, then we can calculate the corresponding fluid saturation rate. And the result is given here in this figure. On the horizontal axis is the fluid injection rate, and on the vertical axis the earthquake magnitude. We show here results for two levels of confidence, 90% and 50%. And for example, if we want to have at maximum a magnitude 3 earthquake, and we impose 90% confidence, then we go here from magnitude 3 to this red curve and select the appropriate value on the horizontal axis and find about 70 liters per minute, which is the maximum rate at saturation, which must not be exceeded in this sense. Okay, I come to the conclusion. What we have done here is we have calculated, or we have estimated, the maximum expected magnitude for induced earthquakes from basic laws of earthquake occurrence, namely the Gutenberg-Richter law and the assumption of a non-stationary Poisson process. All unknown parameters are estimated from the data by using Bayes' theorem. There's no free parameter. And we have found for the Paradox Valley injection site that the magnitude 4.3 earthquake in 2000 lies well, or quite well, within the expectation from past seismicity of about 9 years. Again, given a predefined tolerable earthquake, we can also calculate the maximum fluid injection rate at saturation, or, which is equivalent here in this case, the total volume of injected fluids can be recalculated from this plot. This is not shown here, but can be done quite easily. Future work I mentioned the problem of data availability. So what we need is data, and then we can apply other case studies, and we can also address problems like data declustering and so on, which is not possible in this case, where we do not have access to the catalog. And for more details, I refer to a short note in BSSA, or in the current issue of BSSA, where you can find further details on this work. And with this, I thank you for your attention.
So we have time for questions.
The question is if we can treat non-constant injection rates. In some sense, we are doing this here because you mean non-constant with respect to time. So as I showed here, our injection rate has the following form. And yeah, this is non-constant. This is an increase up to the saturation value. And this injection rate can, in principle, have every functional form. And this is straightforward to include.
Stop and start again.
Yeah, this is a good point. If the injection rate stops, then I can, of course, easily calculate or apply the statistical method. But then we have the problem. We assume that the rate of induced earthquakes is proportional to the injection rate. So if the injection rate stops, then the earthquake activity will stop as well. And this is not quite realistic. We have seen, for example, in the case of Basel, that we have something like a relaxation process after the injection has been terminated. And this is not really governed by this approach which I presented. For this goal, it would be better to use something like an ETAS model or so, where this kind of relaxation can be handled.
Okay. Thank you.
Yeah, thank you.